Okay, thank you, Alistair. So first of all, let me say it's an honour and a privilege and a real pleasure to come and contribute to Dick's, to the celebration of Dick's 80th birthday. So Dick has influenced my research enormously. I have sort of made a career in some sense out of taking some of his papers and working on them and trying to sort of improve some of the stuff. I remember the Karp-Zipser algorithm. I must have written 10 papers on the Karp-Zipser algorithm, and on his patching algorithm for TSP. I made a sort of career out of that. And he'll be surprised to hear that his constructive version of Walkup's bipartite matching algorithm was vital for the proof that 2 in, 2 out is, whatever that means, that 2 in, 2 out is a Hamiltonian with high probability. And the other thing I was thinking is that while Dick's work is characterized by elegance and simplicity, mine is characterized by brute force and ignorance, I think. So my talk will be about something which goes back to Dick's early work on the probabilistic analysis algorithm, and that is the unit square, which is quite an interesting place, the unit square. So I realize that lunch is soon, so don't worry, I will finish. Whatever happens, I will finish. So this is joint work with Wesley Pegden, who's a young colleague at Carnegie Mellon. Okay, so here is the playground. The dots represent random points, and we're basically interested in the length of the shortest tour through these points. Okay, call that Z. There's a classical theorem, Beardwood, Halton, and Hammersley, of God knows when, who prove that with high probability, or probability 1, Z divided by square root n tends to some constant, beta TSP. And this is a very old paper, 60 years, and we still really don't know what this constant is. It's sort of hidden from us, and as far as I know, there's no explanation why. Well, I don't know. I haven't seen an explanation why we don't know what the constant is. That might be something of interest. Of course, the BAH result is more general than this. They got more general distributions, and they also do d dimensions. But this is the basic result. And as I said, price value. Okay, so now we're going to consider a variation on this, in which, so you can think of putting endpoints uniform in the random square and then considering the distances between them as a random embedding of the complete graph, and then assigning the corresponding Euclidean weights. So a natural, when you think about that, if you talk about that, you think, well, why just embed the complete graph? Think of another graph to embed. And so we are thinking about embedding GNP, a random graph. So what you have is you throw the endpoints uniformly at random into the unit square, and then you're going to go around and find a Hamilton cycle or minimum length tour, but some edges are not allowed. Some, you're not allowed to go from I to j, and you're not allowed to go from I to j with probability 1 minus p. And we did some results on that. So we considered, first of all, how does this affect, so if p is very small, then the graph is very sparse, and what it does is it makes it harder to get from A to B, and we analyze that up to a certain point. So you can see there's a lot of symbols there. Just as p is small, it's very different to the Euclidean thing. If p is reasonably large, it looks like the Euclidean thing, and there's a picture. Okay, so on the left you have small p on the left and larger p on the right, and we sort of got it up to about a log n squared factor, but I don't want to. And the proof is brute force. First moment method for the first case, low p, and this is all about jumping from giant component to giant component. And let's see, right? Let's go on. And the next point is what happens to the traveling salesman problem. So we know that if P is 1, which is the normal case, that the length of the tour is beta times square root n. So the question should be, for GNP, it should be beta p times the square root n. That's what you would expect, that the beta would change. The root n won't change, but the beta will just be now a function of p. And so what we weren't able to prove that in any, well, we could prove that if p is constant, then there is a beta p. Okay, it's not completely, well, it does require work. But we could not prove that when p goes to 0. And the problem there is that the usual method is some sort of you just partition it and you use subadditivity. And the problem is when you look at the little squares, when p goes to 0, you've got a different p now relative to the size of the thing. Whereas if p is constant, and you can push everything through. I mean, you come up against some small roadblocks, but you can push it through. Okay, so we can skip that. So we're making progress. So now I'd like to talk about these things which we call Euclidean functionals. Okay, so after the Beardwood, Holt and Hammersley result and Dick's paper on partitioning on the algorithm, Papadimitriou looked at the proof, at least this is what I'm guessing, he looked at the proof and saw that you could push it through for matchings. And so he proved that for the perfect matching problem in the unit square, or the d cubed, there's a beta. And it's the same beta times square root n, and we'll call that one beta perfect matching. Then after that, Still generalized the BHH theorem and showed that that this root n times beta is a sort of, I don't know what the word is, a paradigm or a phenomenon, that there were things called Euclidean functionals. So for the minimum spanning tree, there's a beta MST, and for the minimum length 2-factor, there's a beta 2-factor. And then quite a difficult paper, Homans and Bert-Seamus, showed that if you consider the held carp or the linear programming relaxation, the natural linear programming relaxation of the TSP, that there is a beta HK. Okay. And none of these constants are known. I mean, not to me anyway, as far as I know. And I suppose if anybody comes and tells me now, this is the end of the talk. So these constraints are not known, and they could in fact all be the same. You could in fact have beta MST equal beta TSP, or the beta TSP could be twice the perfect matching. Or the Held-Carp bound could be asymptotically optimal. It could be, but yeah, sure. What's up? Did you know the MST one?
Yes, I'll tell you afterwards.
Okay, good. Okay. Well, that's the end of the talk then. Okay, so let's continue. So we have some refinement. So MST big delta will be denote the minimum length of a spanning tree if we put a bound on the maximum degree. So MST2 would be a Hamilton path. And 2-factor G will be the 2-factor problem where you put a lower bound on the girth. So every cycle in the 2-factor will have to be at least G. And we'll skip the HF, it's not terribly interesting. And all these functions have their own betas. Okay, so the news is that they are different. That the TSP, which is the minimum spanning tree 2, is strictly bigger than minimum spanning tree 3. It's strictly big, and it doesn't go on forever. It goes on to there's some point when you know that in the minimum spanning tree, the maximum degree is bounded. So for like in the unit square, the minimum spanning tree has maximum degree 6. It's something called a kissing number. The next thing we proved was that, so Wes and I, was that if you put girth 3, that's just your standard 2-factor. But if you say it's got to be at least 4, then it goes up. So beta 2-factor 3 is less than beta 2-factor 4, and so on and so on. And what's nice is that if you allow the girth to go to infinity, then the limit is the actual TSP. And unfortunately, well, it doesn't matter really. The held cart bound is beta for that is strictly smaller than the TSP. Okay. And actually, what we showed they're different, but just different. So if we do not even say in the paper that we do not try to optimize. We just leave it at that, because if you actually look at it, the difference is, I have no clue. If I say that there were 10 to the minus 100 difference between the two, I think I'm probably lying. The proofs, really, yeah. So you would not notice a difference in the current universe, right? In a slightly bigger universe, you might, but not in this one. And the matching, so they're all different, okay. And what's the next thing? Oh yes, and then as an application, sort of an unfortunate negative thing about this is that if you were to use just the held cart bound for your branch and bound algorithm, then with high probability, it takes almost exponential time. You have to do a lot of branching to actually, and this is even if I give you the, I tell you what the minimum length tour is, and I just ask you to prove it, that that's the minimum length tour. And it just takes almost exponential time. And 12:15, good. Okay, so the proofs are actually not too, well, I'll say they're simple. The gadget, they're just basically by a gadget. Okay. So the idea is that because we've got a large number of points, right, we have a linear number of little configurations. So here, let me see, what do we have? We have 4 points, right? Let's do this one, right? Yeah. So we have a linear number of places inside the square, which consist of, basically you see a little set of points here, and it's sort of separated from the rest. So everything that happens here is sort of independent of the rest. Okay? And what you would like to do in this situation, if you see, you'd like at the top row, because you're saying the maximum degree is 2, you're forced to do something silly. You're forced for your tree to do the thing at the top and make a path. Whereas really you would like to take the little tree which has a vertex of degree 3. And every time you do that, you'll pay some small, a really small constant divided by the square root of n. So every time you do that, and this happens with high probability n times, order n times, so you pay. And so that's it. And then for every other thing, there's a different gadget. And the gadgets get more and more complicated as you consider more and more complicated functions. So let's see. And there are all sorts of things you have to do. You have to sort of make sure that you can't cheat by coming in to this thing, only going through half the gadget and then going out again. You have to argue that that won't save you. So that takes some more work. And here's the same thing with the factors. You have to do things like this. And then with the factors, now we can see why the constants are getting really small. Okay, so with the factors, we have these gadgets, which we would like really to have 4 cycles, but we're not allowed them. And then we do something, and if we're not careful, we will create 4 cycles. So what we have to do is surround our gadgets by this cloud of points. very close together, and somehow we can use that to force us to show that in fact okay. So we do this gadget, we make this change, and then oh my God, what we've done is we've created some small cycles, but we need these big clouds of points outside, which will turn these small cycles into bigger ones at a very small cost. And we use Dick's patching idea throughout the paper. And then the branch and bound, we just argue that the branch and bound tree, actually it was, yeah, so the natural thing to do would be, so what's the branch and bound algorithm? So you build this tree, and every vertex has some sets associated with it. It's got those things which IV, which is the edges you forced in, and OV, the edges you forced out, and a lower bound. Right? And what we basically argue is that if LV and OV are small, then your two-factor bound, or your lower bound, which is currently it started out bigger than the TSP, it may shrink a bit. Like it'll go up. Sorry, the lower bound will go up. Oh yeah, the lower bound will go up, but it doesn't reach the tour length. Okay, unless LV and OV are large. And even there was a small problem, which we had to, instead of dealing with all the tours, we just dealt with the sort of tours that Dick's algorithm dealt with. Okay, so that took exponential time. This is taking polynomial time. This is good. And then we had to, well, forget that, right? So then just for the last 5 minutes, so this is an idea that Wesley thought up. So here's a claim. Okay, so for there we were looking at, branch and bound, right? And we're saying that if I give you the upper bound, if I give you the minimum length of the tour, but you don't have a good lower bound, then things are bad. So the opposite would be, I give you a great lower bound, which is correct, but I don't give you an algorithm. So you need to have some heuristic, which is finding tours to compare with that. Okay, so there are certain sorts of algorithms, so let's consider nearest neighbor. So the point is, when nearest neighbor meets these gadget places, you can sort of argue that either it does something stupid, or it tends to just go through the nearest neighbor through the gadget. So it's like being nearest neighbor on the gadget. Okay, and it has to do this lots of times, a linear number of times. So it's like nearest neighbor on the gadget. What does this mean? Well, so if we use Christos's NP hardness proof, so you start off with vertex cover, and so inside this big mass of endpoints, there will be zillions of what we call p-sets, right? And some of these will be, and this algorithm, it's like the nearest neighbor algorithm, cannot get it right all the time. Because eventually these peak sets get bigger and bigger for a larger and larger size, and they must make mistakes, otherwise they would solve vertex cover. And so this is a sort of proof that you could probably come up with another proof that nearest neighbor didn't give you a beta root n. But this one sort of tells you that nearest neighbor doesn't give you a beta root n, and actually we can sort of put it into a sort of large class of heuristics, which Wesley calls scale-free. And it's not quite that simple, because there's all sorts of talk about the issue of rounding. How many bits do you need? And stuff like that, which makes the definition a bit ugly, but it's quite nice. And the only thing that's, well, not the only thing, there's two things to say. So first of all, k-opt It's probably, well, we think it's in the class, but we can't prove it. And Dick's algorithm is not in the class because that uses exponential time on the little squares. So Dick is not scale free. I'm not sure if that's good or bad, but yet. I don't know about yet. And here's a picture of Christos's picture. And I can finish. Yes. Oh yeah, and then so you can use some sort of primitive branch and bound and say something bad about that. So there's some open questions. Nothing's very interesting. There's a few of these things which we don't know. I'll skip that. All right, thank you very much. That's not. It's because so there's your paper, right? And for GN for the what we call chi NP, we don't know whether your algorithm still works. You may know, but we don't.
So you do something else.
Oh, for the heuristic to get.
Well, you don't know how to.
Well, for P constant, we can use Dick's algorithm, but for what's it called? For P going to 0. Well, first of all, we don't know whether your algorithm works, and for P going to 0, you can get. Did we? I can't remember, to be honest. This is a year ago. You think your algorithm should work, yeah? For G? Okay. Okay. Really? Wow. 2, 3. Tell me when. Oh, that's an omega. That was some arbitrary function which tends to infinity. It's just that it should be log d to the n over n omega, where omega to d and omega are basically the same sort of thing, right? And so the log-logs shouldn't be there. That's just a bit of the proof. The log-logs shouldn't be there. Well, I don't know, but I assume they shouldn't be there, right? Okay, so that's an omega, right? And this one is this paper's on the first two papers are on my homepage if you're interested in reading them.
Okay, let's thank